Alright guys, so in this video we're going to go ahead and talk about programming, and this is going to be a kind of overall view of programming, kind of the foundations of what you'll need to be able to go ahead and start kind of writing code for yourself. And we're kind of approaching this as the quick start guide, because there are a lot of details and nuances that can go into programming, and they're not all things that are going to be directly related to this. So that's why you may see programming classes or entire college degree programs in terms of programming. So these slides are originally based off of what I got from one of the professors who came in during my Principles of Engineering training session. And Dr. McNeil is a mechanical engineer teaching down in the South Carolina, or the University of South Carolina. Alright guys, in this video we're going to take a look at programming, at least the bigger picture of what's needed to go ahead and get an introduction to programming. It's an important skill. I think pretty much every field of engineering now is going to involve some degree of programming. Some of it's going to be fairly basic, other parts are going to be closer to computer engineering or computer programming, where it is obviously going to be an important concept. But I mention that because the original version of these slides is from Dr. Stephen McNeil. He was still is a professor at the University of South Carolina, where he is in the mechanical engineering department, but he has a good comprehension of what's involved with coding. Alright students, so in this video we're going to take a good look at programming, what's needed, how to get started, some examples of how it's written. But I think this is one of the more important concepts that we're going to cover in Principles of Engineering, because in this day and age I think anyone who goes into engineering, or even most technical careers, are going to have to do some degree of programming. Now some of it may just be writing script within Google, or some of it will just be writing script within Microsoft Excel or Google Sheets, but many are going to be using things like C, C++, Python, languages. They go ahead and communicate to the computers what we want them to do. And I mention this because the original version of these slides comes from Dr. Stephen McNeil. So the original version of these slides comes from Dr. Stephen McNeil. He is a mechanical engineer by trade. He's a professor at the University of South Carolina. But he came in during our programming session and actually gave us these slides and has a good understanding of what's involved with programming. I've obviously edited some more recently to include some other details to help explain what we're looking at. But we have similar philosophies, and I think many people that get involved in programming have the same philosophy. It doesn't take much to go ahead and teach everyone how to program. For a while now, there's been Hour of Code and code.org that make it a point that a simple hour of time and you're going to be able to go ahead and start writing your own programs. The challenge, however, comes from learning how to debug the code, because there will always be problems that arise when you're programming a computer. The reason for that is computers will only do what you tell them to do. They're not going to be reading your mind. And that's meaning that that's not always going to be what you want. Because very rarely are you going to be able to get a computer to do exactly what you want unless you're very, very clear about telling it what you want it to do. A great example of this in a more real-life scenario is Exact Instructions Challenge. There's a video out there, it's not too long, it's kind of worth checking out, and the idea is, how do you make a peanut butter and jelly sandwich? So a father goes ahead and challenges his younger children to go ahead and write the instructions, and he literally follows those instructions. And you'll probably laugh at a few of the things that go on in that video. But it's a great example of the difference between a compiler and what the computer is going to recognize and what you're actually wanting in real life. So, the whole idea is that programming, and when a computer interprets it, it's translating what you write in English, that's loosely defined since different programs have different syntaxes and ways of writing the code, to something that the computer and its hardware is going to go ahead and understand. So for example, if we say A equals 1 plus 2, you and I are able to go ahead and recognize that as A is going to be equal to 3. But for a computer to go ahead and recognize that, it needs to be put into its language. Okay? It's not going to see 1 or 2. It's going to see the binary versions of them. So 0001, 0010 for 1 and 2. So it's putting that information into its adder, okay, the functions built in for it to go ahead and do the calculation. The same way that at one point you had to learn how to do the addition yourself. Okay. Puts 2 into the adder. It then runs the command to go ahead and process the information in the adder. And then it translates that, transferring it into the memory that is dedicated for the value of A. Older computers literally were showing you the binary versions. Lights were on or lights were off. Now, obviously, we've become a lot more advanced than that, and we've got graphic interfaces or even command line, but it took us a while to get to that point. And there's a lot of history that goes into many of these concepts. So when it comes to computer languages, there are many different languages. Just a few of the ones that come to mind. Fortran, Basic, C++, okay, which is what we're going to focus on. Python, Java, JavaScript, some of them like Cobalt. You know, some of these languages have been around since the 50s and 60s when digital computer really kind of started getting a lot of commercial growth. Some languages have only come out in the last few years based on the needs or the abilities of cell phones and digital devices. So as long as the language is serving a purpose, it's still going to be around. Cobalt, one of the oldest languages out there, is still used, and they have trouble finding programmers to go ahead and do it, even though there's still a required need for it. So, as I mentioned, C++ is going to be the primary language that we're working with. It's one that most computers, operating systems, and software programs are going to run, but it's also a good one when you're getting close to the hardware. So this is what we would have used if we were going to be working with the VEX Robotics programming, or Arduinos, which is what we're going to get a little closer to. So the basic things needed. The first things are the instructions for the compiler. This is basically setting up, you're basically declaring what the language is and how it needs to start operating. From there, you start getting into the actual program itself. And in C++, all of them are going to have what's considered a main function, a main purpose. And this is going to be the foundation of your code. Now, some information is going to get reported back, regardless of how you set it up. So you need to identify what type of information it's going to be sending. And then these curly brackets are to go ahead and help identify where the beginning block of code is going to be and where the end is. This is another important concept as you get into more complex programs and you start having multiple pieces. And then you of course have the block of code itself. Okay? These are the literal instructions you're giving the computer to go ahead and do what you want. Okay? So in this case, this is more of what you would do on a desktop computer and have it attached to a screen, and it's able to tell you, hey, I'm a working program. Now, in C++, okay, another important concept to remember is every line of code, every instruction needs to end with a semicolon. Okay? So we actually see several of those available. Okay? So we see another one down here, another one down here. Okay? And that's going to be an important concept. Okay? So, same language, C++, but now we're looking at it how we would have seen it with RobotC. Okay? Same concepts. Okay? We have the initial directions for the compiler, setting up the hardware, setting up the basic parameters it's going to need. And then we can get down to the main program. Okay? And it actually names it as task main. Okay? It then gets into the the type of information that it's doing, where the code is going to start and stop, the code itself. Okay. Now you'll notice that there's a big green blob, okay, and those are comments. Okay, and this is another aspect of programming that is often overlooked, but still a very critical role. Comments are basically things that you can put into the same code document that the computer will compile. But comments are basically things that the compiler will ignore. It'll skip over them. Okay? So there are a couple of ways of going ahead and writing them in C++. Okay? 2 forward slashes will go ahead and say anything from this point on in this line is going to get ignored. As soon as you hit the return key, you're into a new line, and it's going to start interpreting that code. /* asterisk and asterisk / basically sets up the starting point of a comment and the end point of a comment. So that's the tool that you want to use if you're going to go ahead and write multiple lines of code. Now, the last little example is within TinkerCAD circuits. Many of you probably remember that from our early electrical projects. And in this case, okay, we're seeing the same thing. Okay? So we're seeing the start of the program. Okay. We're seeing the code itself. Let's actually step back and add in a couple more details that I didn't necessarily animate. So the last example is when we start getting into TinkerCAD and circuits, where many of you probably remember when we used it for electrical circuits, but we can also include Arduinos, which is a microcontroller similar to the cortex of a VEX Robotics. So we can see the start of the code. Let's see. Let me go ahead and add in a few more. So the initial setup is actually in this own block, okay, where we're setting up pin information and basic procedures that it needs to be aware of. Okay. We still declare the same thing, what type of information will this send when it's done with that part of the program. It's not something critical for hardware, but it's something that you often use with software. And then we also have the starting curly bracket. We have the semicolons at the end points. Okay. In terms of comments, we have the 2 forward slashes to comment everything else out in that line. And then we have the ones where it's multi-line comments, where we have the forward slash and stars. Okay. So the other nice thing about the Arduino circuits, though, is we can have you programming with blocks, okay? Which means that you can eliminate some of the common errors that we'll talk about in a little while. So within programming, there's a lot of things to kind of know about. Probably the first one. So probably one of the first things to know about are variables. Where do you actually declare information? Where do you store it? And there are different ways that you can approach this. Okay? INT are integers, basic numbers. Char, C-H-A-R, is to identify just a single letter, a single character. Float is when you start dealing with decimal numbers. Okay? Now, the way that you set up the variables is going to vary. Okay? Some things like X, Y, and Z are good for counters, just basic numbers. Steve, Brian, I'm not quite sure what those are good for. But in this case, we've got them setting up as characters. Float, first, second, and third. Again, some of the things that you should be aware of in variables is a good practice is to give them good names. Okay? Part of that is looking out for typos, because in C, C++, variables are case sensitive. So if one part's capitalized and you forget to do that later on, it's going to try and find a different variable. Also, it's an important idea to reuse them. So when I say it's good to think about good names, okay, X, Y, and Z, those are good common ways of identifying a value that you need to keep track of. Keeping count of how many times has that part of the code run through. Okay. Count Dracula, Chocula, Monte Cristo, those, while clever and still technically counters, are going to be harder to remember and could be easier to go ahead and have typos. In terms of things like Steve equals the letter C, maybe that's too long. Okay? Now, we do want to be descriptive, but we want it to be something practical at the same time. So when we're dealing with a robot, having a integer to identify which port, which pin of the controller we want to use, identifying that with left motor is literally giving it an appropriate name. Another important concept in programming is math, and this is why I actually have seen a lot of math classes, especially college level, where they start incorporating some programming into their math curriculum. So you guys already remember, well, in terms of programming, left equals right. So whatever information you have on the left, okay, is going to be equal to whatever's on the right. Okay? So it's a little bit of a flip from what you've probably seen in your math classes, where usually we've had the problem on the left side of the equation to enter the final value. Okay? So the correct form is going to be a equals 1 plus 2 to actually put it into a variable. This is probably going to generate an error. Okay? Now, in terms of symbols that we use within programming, plus, minus, the asterisk for multiplication rather than an X. We use a / for division, a caret for an exponent, and then we've got an example problem down here. So a equals 3 plus 6 times 2 divided by 8 times 9 raised to the third minus 2. So in traditional practice, that's it. Alright. So another important concept in terms of programming is math, and I've actually seen plenty of math teachers, especially at the college level, incorporate some programming into their curriculums. So some of this is basically assumed knowledge. Okay? Addition and subtraction, plus and minus, multiplication, division, asterisks, and the / raising to an exponential power. We use the caret symbol, but probably one of the differences between core math and what programming expects is the left side is where the solution is, and the right side is where the problem is going to be written. Okay? So in terms of a equals 1 plus 2, that means that we'll do 1 plus 2, and then that information gets stored in A. Whereas 1 plus 2 equals A, that's probably going to generate an error in a computer program, even though you'd be able to go ahead and identify A as the same thing. Okay? So correct form, left is where the comment or the variable should be, and then the right side is where the problem is. Now, before we tackle this problem, we're going to go ahead and get into the order of operations. Okay? And again, quick review. Parentheses is first, exponents second, multiplication, division, addition, subtraction, left to right. Okay? So in this problem, okay, when we look at it, 3 plus 6 times 2 divided by 8 times 9 raised to the third minus 2. First thing that we tackle is that 9 raised to the third, and then we start left to right for multiplication. So 6 times 2, 6 times 2 divided by 8, and then that times 9 raised to the third, and then we run the 3 plus whatever we found minus 1 at the end. And because 9 raised to the third is going to give us a really big number, it's no surprise that A in this case equals 1095.5. But if we put in those parentheses, which I've encouraged you to do when you write out your formulas, A equals 3 plus 6, 9, times 2 divided by 8, 0.25, times 9 raised to 3 minus 1, so 9 raised to the 2, 81. So this makes it a little easier to go ahead and tackle the problem, and it makes a pretty big difference. We went from nearly 1100 to 182.25. So in programming, if statements, okay, how do you make a decision? Okay, this or that. So if statements basically ask a question, okay, what is the condition? What is going to be answered as a yes or no, true or false? Okay? And if that answer is true, okay, it does one set of instructions. Okay? Otherwise, it will say no, and it'll do a different set, or it'll skip the instructions that were given. Okay? So if A and double equal signs are they equivalent? So if A is the same as B, C equals 6. If they're not the same, the else portion, C equals 7. Okay? Now, when you're asking these questions, okay, the goal is make it a yes or no type question, true or false. And since it's often based on mathematical or stored values, okay, this is where we use greater than, less than, greater than or less, or greater than or equal to, less than or equal to, or not equal to, as our test procedures. Okay. Another quick concept are loops. Okay. How many times do you want something to repeat itself? Okay. And there are 3 ways that we can go ahead and handle this. The first and probably most reliable way, kind of the most self-contained approach, is using a for loop. Okay? So within the for loop, you basically tell it what is the initial value of your counter going to be, how many times are you going to want it to run, what's the condition, okay? So as long as that counter is still true, go ahead and repeat this, and each time we need something to change. Okay? So it could be a variable value, it could be something else. Okay? So an example of this is basically if we want you to count to 10. Okay? For x equals 0, so we start with 0, and as long as it's less than 10, it will keep running, and each time it runs, x is going to be equal to x plus 1. So in this case, first time, x equals 0. We say, okay, we're going to add the next one. X equals 1. Do it again. X equals 2. X equals 3. And it'll keep going through that. Okay. Now, recognizing that a computer and a person are going to be different things, this would actually end at telling us that x equals 9, okay? Because at that point, 9 is going to be greater than 10, okay? Or sorry, 10 is going to be greater than 9. But 10 is going to be equal to 10, and that's not part of the test procedure. So again, for loops tend to be self-contained, fixed number of repeats. There are some ways of escaping out of that, more advanced programming techniques, but it's a good way if you know that you want something to happen 10 times or 20 times. Okay? Another type of loop are where it's expecting changes to happen. Okay? Could be happening before it starts going into the loops, but there's going to be something tested during the loop to see if something is still true or still false. So while loops basically does the test before the code is executed. Okay? So your code will not always run. If it doesn't pass that test, that code is never going to run. But a do while will basically do the instructions and then do a test. Okay? Great way of looking at this is the Roadrunner and Wile E. Coyote. Okay? So Roadrunner is going to be checking the ground. Okay? And as long as they're not over the edge, he's going to keep running. He gets to the edge, he's going to stop. Okay? Whereas Wile E. Coyote is basically just going to keep running and running and running and running, and he'll run over the edge before he does the test to see if the ground's still underneath him. Okay? So it's an approach to kind of think about it. In my experience, it's much more often that you're going to be using the while loops rather than do while, but if you need to make sure something runs at least that one time, that do while loop could be a good option. Functions is when things start getting more complex. This is usually towards the end of a programming course on its own, but it's a good thing to kind of keep in mind in that when you're writing a program, try and write it down into small segments, things that you can easily remove, or if it's something that you know that you're going to have to repeat more than once. So in this case, multiplication. We may have multiple problems that we want to multiply. And by creating a function where we can say, hey, take this value, and then multiply them and tell us what it is. Okay? Some of you may remember that in Excel, we've used functions to go ahead and tell us what's the standard deviation, or used a function that is explicitly designed to take information and create a chart. So, when you're starting a program, okay, there are all sorts of problems that can pop up. Okay? The most common type of mistakes, though, okay, is you start programming without thinking. Okay? The best policy when it comes to programming is plan ahead. Okay? Pseudocode, where you're writing vague instructions before you go into the details, something that's closer to what a human would process. It's a good way to start. Some will use flowcharts to go ahead and give them that initial map. Okay? But if you don't do some planning in advance, you're going to end up with a program that's going to be a lot of a mess, and it's going to be hard to track down what went wrong. That gets into the concept of writing code in an unstructured manner. Okay? When you're starting to name your counters as Dracula or Chocula, okay, think about how you're going to approach it. Okay? Set up some good practices. Have a plan for how you're going to name your variables. What naming structure do you use? Can you set them up as functions? Okay? So when it's structured, okay, you're usually dividing it into bite-sized portions. Here's a part of code, and if you remove it, you can test it independently of everything else. That makes it easier to go ahead and troubleshoot some of your problems. Okay? And as mentioned, use variable names that mean something. Don't just get clever names. Okay? So when you start facing problems, and it's not an if, it's a when, okay? There are two types. The first is compiler errors, problems with the code that you wrote. So the first listed compiler error, okay, and most compilers will give you a list of all the errors that happened in your code. The only one that will absolutely be a real error is the first one listed. After that, maybe it's something that was written, maybe it was the lack of that semicolon, maybe it was a typo. But when that one error happened, it can cause other errors. Okay? So everything underneath it may not be a problem. So always solve the first one, compile the software, see if there are other problems, okay? And only take on the first one. Very rarely do I think it's a good policy to correct more than one error at a time. Okay? It's one thing if it's a typo, or if you know that maybe you missed a couple of other semicolons, you can take a glance through those. But in general, solve the first problem, and sometimes that'll solve everything else. Okay? Now, kind of the exception to solve the first error, because it'll be immediately above that line or as that line, is the curly brackets are an easy thing to forget about. Okay? Any one that you open needs to be closed. So you may need to check towards the end of the code, because technically those curly brackets are on the same line. Run errors. This is probably where you're going to have more problems if you're using the drag and drop code blocks. And that is work from the top down. Okay? You need to figure out how to start thinking like the computer. Okay? Don't assume anything. Okay? Don't assume that you got the function written down correctly. Don't assume that you have the variables typed correctly. Don't assume anything. Okay? When those check out, that's when you need to start testing it in small bits. Okay? Comment something out and see if it still works. Do a test. Have it give a report. Okay? Even though we're programming hardware, we can still have it send text messages back to the host computer, at least with the Arduinos, and you can start seeing, okay, it got to this point where it told me, yes, I'm still alive, I'm still good. Now, like I said, there's a lot that goes into programming. I've only touched a small portion of it and tried to give you kind of the good starting grounds. But websites like cprogramming.com have a lot of tutorials. There are other sites that provide communities where you can get input and get some advice. And what we're going to be focusing more on are things like the Arduino programming language. So on Arduino's website, they have both a reference page where you can see what a line of code is supposed to look like, what the functions can be, as well as their set of tutorials, which are a good way to get started. And then we have some that have grown beyond just what Arduino has provided as their foundations. Things like Sparkfun and their experiment guide give you some instructions to the point where you're making your own version of Simon Says with an Arduino and a few programs. So in another video we'll talk about kind of the approach to programming and what we can actually do in TinkerCAD. But I know this is a longer video with a lot to process, but as I said, programming is one of those skills that I think everyone in the room, everyone in the class is going to use at some point, because think about how much you use a computer and how many times you wish, well, maybe if the computer would do it just this way. Programming is how you go ahead and wish for it and where you can actually make it happen.